now I will start with the intro. So through this project, we were required to find for the moles of the liquid and the vapor phase. Other than that, we were also required to find for the mole fraction of the liquid phase and the vapor phase. This process occurs in a flash separator equipment which used to separate the liquid phase and the vapor phase of a mixture, which is in our case a methanol and water mixture. This equipment was also used in the chemical and energy industry. As for the objective, the first one is to design a flash separator to separate a mixture of methanol and water. The second one is to review the processes and typical process condition, which consist of overall composition, operating pressure and temperature. The third one is to calculate the moles of the liquid, moles of the vapor, liquid phase mole fraction, and vapor phase mole fraction. So how does it work? A high-pressure liquid mixture, often a saturated liquid, will enter the flash separator. The separator will then maintain at lower pressure, and as the pressure drops, part of the liquid will flash or vaporize rapidly. The resulting vapor and remaining liquid will naturally separate due to the differences in density. The vapor exit from the top and the liquid exit from the bottom. Before we start our calculation, we will first need to make clear all of our assumptions. The first one is the mixture of the methanol and water will have to be considered an ideal solution. The second one is the system operate in a steady state condition. The third one, the flash distillation process of the mixture is considered to be 100% in efficiency. The last one is the mixture is an equimolar. Before we start our calculation, we will also need to find all of the required information of the methanol and water from the table B1. To find the operating temperature, all we do is apply the formula of average. What we do here is we find the Tn of methanol and water from the table B1 and then we divide it by 2. And then from that, we get the 82.4 degrees Celsius as our operating temperature. For the operating pressure, we only apply the formula of the Entwin equation from the table B2. And as you can see here, for the methanol, we use ln P set equal to 60.5785 minus with 3,600 338.27 divide by 82.4 plus 239.5. And then we solve this, and then we will get the pressure saturated. The saturated pressure for the methanol is 195.5860 kilopascal. And as for the water, we get the saturated pressure is 52.2322 kilopascal.
For bubble point, we use the mole fraction of the components by multiply their saturation pressure. Since we have 50-50 mixture of the methanol and the water, so the calculation becomes like this. So we can see there is 0.5 times with 195.5860 plus with 0.5 multiply with 52.2322, which gives us a bubble point pressure of 123.9091 kilopascal. So next, for the dew point pressure, we use the inverse formula, summing up mole fraction over the saturation pressure. Substituting the same value given us a dew point pressure of 82.446 kilopascal. Finally, the operating pressure is the average of those two values, which is 123.9091 plus 82.4466 divided by 2, which is we can get giving us 103.1776 kilopascal. This confirm that both phases, which is vapor and liquid, can exist, make this suitable for flash separation. To begin, we calculate the equilibrium ratio Ki for each component. The formula used Ki equivalent to Pi saturation divided by P, which is pressure. So where Pi saturation is a saturation pressure of the component and P is the system pressure. So for methanol, the K value is Km, which is equivalent to 195.5860 divided by 103.1776 equivalent to 1.8956. And for the water, Kw, so equivalent to 52.2322 divided by 103.1776, which is equivalent to 0.5062. Calculate the amount of the vapor formed during the phase separation using the Rashford-Rice equation. The sum of the Zi Ki divided by total of 1 plus V bracket Ki minus 1 equivalent to 1. So that is Zi is the feed mole fraction of each component and V is the fraction of the feed that become vapor. So substituting into the values, so as V equal to 0.4543 mole of vapor. The remaining amount from the liquid phase, which is L equivalent to 1 minus B, is equivalent to 0.5457 mole of liquid. Finally, we determine the composition of the each phase. First, the vapor phase mole fraction are the calculating by using Yi equivalent to Ziki divided by the total 1 plus V bracket Ki minus 1. So for the methanol, we get the Ym, which is 0.6737, and for the water, Yw equal to 0.3263. Those values show that vapor phase is methanol rich. Yeah. So next we calculating the liquid phase mole fraction using the Ki, Xi equal to Yi divided by Ki. So for the methanol, Xm equal to 0.6737 divided by 1.8956 equivalent to 0.3554. For the water, Xw equivalent to 0.3263 divided by 0.5062 equivalent to 0.6446. So this confirm that the liquid phase is water rich. In conclusion, for the entire calculation, this phase separation successfully separate the mixture, producing a methanol rich vapor and water rich liquid.
The picture shows a PXY chart for the mixture of methanol and water. The graph is generated at T equal to 82.4 degrees C. For the S1, we decide to have the interval by 0.1. The P2 set is 52.2322 kPa, which is for the water component, and the P1 set is 195.586 kPa, which is for the methanol component. For the value of pressure and Y1, we calculated using the equation shown. This graph illustrates the variation of equilibrium pressure with mole fraction of methanol in both the liquid phase and the vapor phase at a constant temperature. The blue curve represents the bubble point curve, while the orange curve represents the dew point curve. The larger difference between the X and Y values indicates greater relative volatility, showing that methanol is more volatile than water. Next, the picture shows a TXY chart for the mixture of methanol and water. The graph is generated at P equal to 103.1776 kPa. We calculate the TB, P1 set and P2 set by using Antoine equation. At P equal to 103.1776 kPa, we get the value of T1 set equal to 65.16 degrees C and T2 set equal to 100.51 degrees C. The step size interval between the T1 set and T2 set is 5. For the value of X1 and Y1, we calculated using the equation shown. This chart presents the boiling behavior of the methanol and water mixture at constant pressure at 103.1776 kPa. The blue curve represents the bubble point curve, while the orange curve represents the dew point curve. The area between the two curves represents the two-phase region, where both vapor and liquid coexist in equilibrium.
So this is a process flow diagram. The water and the methanol entering the flash column is equimolar. So we assume that the number of mole while entering the flash column is 1 mole per hour. So from the calculation, we find out that the number of mole for vapor phase is 0.4543 mole per hour, while for liquid phase is 0.5457 mole per hour. While the mole fraction in vapor phase for methanol is 0.6737, while for water is 0.3263. For the mole fraction in liquid phase, the methanol is 0.3554 while the water is 0.6446. For the first question, why is the result make sense? The result makes sense based on the principle of vapor-liquid equilibrium. The methanol is more volatile than the water and tends to vaporize more easily. So that this explains why the vapor phase is richer in methanol while the liquid phase contains more water. So this distribution of components align with the Rod's law, which state that more volatile components are more abundant in the vapor phase. So the mole amounts in each phase sum up to approximately 1, indicating that the mass balance is maintained. For the second question, how changing of temperature and pressure may affect the flash. So the effects of temperature and pressure change on the flash separation are significantly because they directly influence the phase behavior. So when we increase the temperature, it will increase the vapor pressure of the components and making more of the mixture vaporize, which result in a larger of vapor fraction. As for pressure, while we decrease the pressure, it promotes flashing by allowing more liquid to vaporize, especially for volatile components. Therefore, by adjusting the temperature and pressure, the extent and composition of vapor-liquid separation in a flash process can be controlled. So these are the limitations for the flash separation. It is only effective when components have large difference in volatility. We need to assume that instantaneous vapor-liquid equilibrium, which may not be fully achieved in practice. It is inefficient for separating components with close boiling points. It is not suitable for complex multi-component mixture without additional separation stage. It is highly sensitive to temperature and pressure change. It may require high energy input. The mass transfer limitation can reduce separation efficiency in real systems. In conclusion, the flash column of the methanol water mixture worked as expected based on vapor liquid equilibrium. Since methanol is more volatile, it mostly went into the vapor phase while water remained in the liquid phase. The values that we calculated were matched with the theory predicts, showing that the process was done correctly.